Welcome PCS members and friends to our PCS IBS seminar. Today we have a pleasure of hosting Professor Chen Jing-Yuan from Tsinghua University, Beijing, China. And our scientific host today is Zung, who will introduce our speaker.
So thank everyone for coming. So we are very happy to have Jing-Yuan Chen from Tsinghua University. Jing-Yuan was studying his PhD in the University of Chicago under supervision of Professor Dan Tangser. And after that, he go to Stanford for a postdoc under supervision of Professor Jing-Yuan. After the first postdoc at Stanford, he moved back to China and being the faculty at Tsinghua University at the Institute for Advanced Study. So Jing-Yuan research is quite broad. He's studied both condensed matter problem. For example, what we see here today is some transport problem. He also have some very important work in high energy physics. For example, like the current kinetic theory in particle physics. And he also did very important work in lattice model of quantum field theory in the lattice. And Jing-Yuan will stay with us for a week. He will give 2 seminar talks. The seminar talk today will be on like more condensed matter side. On the other seminar talk on Thursday will be the borderline between the condensed matter and high energy physics. And let's welcome our speaker.
Thanks, Son, for the introduction. It's very happy to be here today and share some of my works on the thermal transport, which are very experimental data-driven research works. As Sun helped me advertise, on Thursday I will talk about some more formal works with lattice models and topological operators. But today's talk will be completely driven by experimental data. It's a purely phenomenological work. And these works were done, so there are 2 earlier works done with Steve Kivelson and Xiaoxi Sun a few years ago when I was a postdoc at Stanford, as well as after I came back to Tsinghua. And then there's a more recent work on another material with a very talented student, Zheng Duo, and also with Xiaoxi Sun, a previous collaborator. So this work will be concentrated around these 3 papers. So thermal transport has, in the recent years, become an increasingly appreciated probe for unusual physics. But unusual physics, it means to look for things that people did not expect before, or more some exotic systems like topological stuff or not very well understood stuff, as well as some unexpected results. And the idea of thermal transport is very simple. So it's illustrated like this, where you have a sample material here, and then you have some wire that is generating some heat power on one end, and also draining some power on the other end. So this Jx can be understood as some heat current. And then you measure the heat current only runs in the x direction, and then you measure the temperature drop in both the x direction and y direction. And then the coefficient, you have some longitudinal coefficient, which is the longitudinal thermal conductivity, and the transverse coefficient, which is the thermal Hall conductivity. And in particular, because in the experiment, the power is only being sourced and drained in the x direction. So in the y direction, the current is 0. But overall, you can just from these measurements, you can determine the values of kappa L and kappa H. So this is a thermal transport experiment. And why is it becoming so interesting in the recent years? First of all, of course, there is some advance in experimental techniques, so that some things that previously could not have been very nicely measured is now measured more accurately.
how you fix the thermal heat current.
You just measure how many power is being dissipated. But how to make sure all the energy went into the sample depends on how well insulating you make the environment. Yeah. But I'm not an expert in experiment, but that's a general idea. Yeah. So why is it becoming increasingly appreciated? Because it has this very big advantage. That is, all the degrees of freedom has energy. So all of them carry the heat current. It is an advantage because compared to the traditional electric transport, not all the degrees of freedom couple to electricity, right? Not everything is charged. So the electric transport can miss some of the important degrees of freedom. But all the degrees of freedom has energy, so it has the disadvantage. But it also brings us the difficulty for the exactly same reason. Because all the degrees of freedom has energy, so it's very hard to distinguish what is contributing what in the thermal transport. So that leads to the difficulty. And that's why phenomenological work in this field becomes particularly important and useful. And I would want to say one motivating background why the thermal transport has becoming heated in recent years is because the topological phase with a quantized thermal Hall effect has been observed in particularly in the fractional quantum Hall systems. It's a very difficult experiment because it's a purely 2D system. So the heat current involved is very small, has to be measured very accurately. But this gave a very strong, I think this thing is out of battery somehow. I can still use this, but I'll use this to point. So this is in the 2017, in fractional quantum Hall system, which is a topological base, the quantized thermal Hall has been observed and is considered a very important breakthrough in the field. However, I want to emphasize that while this is the motivating background for people to become more interested in thermal transport experiment, so far after that, it doesn't seem to apply to other cases, although it is desired for other cases. But so far, it doesn't seem to apply to other cases. But what happens in the other cases, we need to analyze that. So that is why we are doing phenomenological work in this field. And right, so I will talk about some recent experimental findings, in particular in some important materials, and how we analyze the phenomenology of the thermal transport in those materials. And these materials include, there are three important materials. And for these two materials, I'll focus on the thermal Hall transport because their longitudinal thermal transport doesn't have anything weird in general. So, but their thermal Hall effect is unexpected. And for this other material, both the longitudinal and the thermal Hall transport are very interesting. So I'll focus on these three materials. And these three materials are all very important materials. The simplest material among them is the STO, strong stream titanate, which is a widely used paraelectric perovskite material in both application in daily life as well as in condensed matter research experiments. And a second material is very important for being a high TC parent material. That's a lanthanum cuprate. And this third material is very important because people speculate that it is a candidate for a Kitaev spin liquid. And there is some legitimate reason to believe that it has some terms in the Hamiltonian that coincide with the terms that Kitaev wrote down. But whether this material really exhibit the spin liquid phase is still debatable, and I think probably there's no evidence for that. But anyways, this is also a material that's being heavily studied. So these are three very important materials that all have very interesting thermal transport phenomena. And as a summary of our theme that we concluded the following themes after studying these materials over the past few years. And that is very different from what people expected in the past. In particular, it turns out that people who work with condensed matter usually think phonons are not very interesting. Phonons are, of course, there. They are sometimes important, maybe in the BCS, but the phonons themselves are usually not very interesting, and you don't want to discuss about them too much.
Why not? Because I thought that phonon is very important for thermal transport.
Yes, but it's important for thermal transport, but they doesn't seem to have very interesting behavior. It's thought that everything about phonon has been well understood. And it turns out that phonons have very interesting behavior that people did not expect before.
Like, very curvature.
Yeah, it will be related to that, but it has more than that, right?
This phonon and some kind of excitation is already coupled.
Right, right.
Separation is not easy.
Yes, yes, that's why we need to study this, and this why these are very unusual behavior. Because if right, so our conclusions, general conclusions are that phonons are more interesting than naively expected, and moreover, there are these low energy defects or extended defects, or maybe other degrees of freedoms that can couple strongly to phonons. And as you said, the coupling is not easy. And right, but once they couple strongly, it will lead to this remarkable phenomena. And that's why this phenomena is not always seen in all materials, but only in certain materials, but not all materials. That's why we need to analyze them more carefully.
Do you consider the Magnon contribution of some?
Magnon? Yes, it will be related to that. Yeah, I will mention that in particular in this material, right?
But the high TC is also magnetic.
Right, but we don't think it's relevant for these experiments, right? But in this one, we'll discuss the relation, right? And right, a final theme is to experimentalists is that now that from these phenomenological studies, we can conclude that phonons interacting with these somewhat unusual defects is very important. So we call for experimentalists to actually more directly detect these defects. So these are the general themes that we concluded from this particular phenomenological studies. But each material requires more specific study, of course. So let's start with the special thermal Hall effect in these materials. So let's first review a little bit of the history of the experimental observation. So there is a surprise in 2019 that an unexpectedly large thermal Hall effect has been observed in the cuprates under a magnetic field. And in particular, the original motivation is to look at the strange metal phase of the cuprates, which has been speculated to be related to the high TC mechanism. And then in the strange metal phase, they found that the thermal Hall coefficient has a very large deviation from what you would expect from the Wiedemann-Franz law for the electrical degrees of freedom in the strange metal.
Deviation from Wiedemann-Franz law is quite common, right?
Right. So at the beginning, they thought the deviation is due to its being a strange metal, so that the charge is not a Fermi liquid, but something very exotic. But then they did more experiment, and they found even in the insulating phase.
Just maybe you can remind, Wiedemann-Franz law, it's a relation between usual conductivity and thermal conductivity.
Right,
yes?
right.
It should be proportional. In usual case, it's proportional to temperature.
Right. Right. So they found large deviation from that. So at the beginning, they thought maybe the strange metal is just very different from the usual electric transport. But later, they found even in the insulating case, where there's just no strange metal electrical degree of freedom anymore, there is still a very large thermal Hall effect. So that means that it has nothing to do with whether the strange metal satisfy the Wiedemann-Franz law. It's something more general in these materials themselves, rather than.
That's very easy way to violate the Wiedemann-Franz law.
Right.
If you have the system have two tier quasi-particle, then
Right. So it has nothing to do with the strange metal, really. But the original motivation was to look for that. That's why people started doing the experiment. But then they found even in the insulating case, it has that. So it's unrelated to Wiedemann-Franz law. And it's found here. And at the beginning, it motivated a lot of theoretical proposals such as even the insulating phase of cuprates may be highly non-trivial and maybe some topological or emergent degree of freedom. But all those proposals, after our analysis, we found them very hard to fit with data. You have to be very contrived, very artificial story to make that work.
Sorry, what is GOF?
Degrees of freedom.
Degrees of.
Yes. It's a very common shorthand that I will use, yeah. And further experiment confirmed that there's really nothing unusual related to whatever emergent things in cuprates. Because in the same year, this unexpected large thermal Hall has been observed in more insulators under magnetic field. And in particular, in the Banyas groups, they did the experiment for strontium titanate, which is a relatively well understood, simpler material that is widely used in condensed matter. And even in there, a very large unexpected thermal Hall effect has been observed. And then by this further experiment, as well as our theoretical phenomenological analysis, we confirmed that this is to be attributed to the phonons. So these are phonon thermal Hall effects. And we will elaborate on our theoretical proposals. And we'll explain why people didn't think about phonon at the beginning.
So how you can confirm that the phonon contribute more than?
Yeah, I'll explain later. Right. That's the whole point. Because in the past, people think phonon should not be relevant at all.
If you, after you confirm that phonon will be the most important thing.
Yeah.
All of the material in the cell, right?
Not necessarily, but what happened to that?
It is related, it is related to the topological work.
Right. So if photon can contribute, then it's in future experiments, you need to be more careful, analyze the phonon possibility. But it does not mean it's always phonons. But it means maybe in some materials, phonons can have a large contribution. In the past, people think phonon will not contribute anything observable.
Sorry, will you show more details on experiment, or you can just?
I will show more detail.
You will show, yeah, because what temperatures are talking about?
Yeah. That's what I'm going to show in the next slide.
So what surprised me that why people didn't consider phonon?
I will explain that.
Okay.
Yeah, that right.
Very strange.
Right. People have a good reason to not think phonon, but we found that's not completely legitimate. Right. So let's first review these two experimental data. So first of all, a thermal Hall effect is time reversal odd. And the time reversal oddness comes from the applied magnetic field, right? Otherwise, the system is time reversal even, and there will be no thermal Hall effect. And under the applied magnetic field, it is found that the thermal Hall effect is linear in the magnetic field. If something is linear in the magnetic field, then it seems there is no phase transition due to the magnetic field, right? If the thermal Hall effect is due to some phase transition or the magnetic field inducing some new state, then the effect usually should not be a linear sort of response, right? It should not be a linear. So being linear in the magnetic field seems to suggest the phenomenon should be something relatively simple to understand, right? Because it's linear, right? It's rather than some phase transition or whatever. Okay, and if you look at the data for both materials, they are indeed very much linear. But what's surprising is the following. They are very large. By saying large, we have two standards to say why it is large. There are two different standards. The first standard is if you consider one atomic layer, so think of it as a 2D layer of atoms, then it turns out that for a 2D system, there's a natural unit for the thermal transport, which is this unit. So by quantized thermal Hall, it means quantized in this number, okay? So quantized thermal Hall means it's an integer multiple or fractional multiple of this number. So this is a natural unit for thermal Hall transport in 2D. And by large, first of all, it means in each layer of atoms, the size, like if you go to large enough magnetic fields, it can be a few times larger than this natural unit. However, it's very strange because it's linear in the magnetic field, and the magnetic field is very small. The magnetic flux per unit cell is 10 to the minus 4. Even when the magnetic field is like 10 Tesla, in the natural unit of the lattice, is 10 to the minus 4. So the magnetic field in the natural unit of the insulator is very small.
So the sample is a bulk or 2D?
No, it's not 2D, it's 3D. But we can compare it with each layer of atom. And
I Captain, what is the talking rate?
what?
What is your talking rate in this?
What is the what?
X value?
The doping?
Yeah.
This is a P equal point.
At the time, this is SDW state or?
Oh, so this data can be there even when it's undoped. When it's completely undoped, the data looks almost the same. Yeah. So that's why people originally thought it's related to some strange metal, but later it found it's unrelated to that at all. So, okay.
Do you have this number in mind? For example, if I take just a simple copper, what will be my coefficient at like 80 kelvins or something?
A simple material.
Yes.
Right. That's what I'm going to show right now. Another reason we think it's large, first it's large compared, so it's order 1 in the natural unit, but the magnetic field is 10 to the minus 4. So the effect seems to be very large, even though it's linear in the magnetic field. And the second way to think that it is large is that the whole angle, the kappa H over kappa L, is 10 to the minus 3. And if you do a simple insulator, for example, you can do like salt that you eat, sodium chloride, it has some ions, right? The ions have some charge. So when there's a phonon that moved ion, maybe there can be some coupling to the magnetic field. And you found the whole angle is 10 to the minus 10. So maybe that answers the question. In a usual insulator, it's 10 to the minus 10. But this ratio here is 10 to the minus 3. It's way larger than the
Usual
usual.
data here not linear in T at small temperature, right?
Not linear in T.
And not linear in one pure small temperature.
It is, right? It's linear.
On the left hand side
The left hand side.
It's also linear.
Small,
for small.
it's linear.
Right, it's linear, right? So only for larger, it becomes not so linear. Yeah. Yeah, so it's large by 2 standards, right? Large compared to a natural unit, especially when the magnetic field is small, and also large compared to a naive analysis for usual insulators. That is why people in the past didn't think phonons are related to thermal Hall at all, because it's this small, right? But now we found that it's much larger than the naive expectation for phonon contribution.
Why it's not constant on magnetic?
Okay, right. So first of all, for example, actually this data in this plot, it goes to 14 Kelvin, but it can also go to a few Kelvin, like below 5 Kelvin and so on. The magnon in LCO has a gap of 50 Kelvin. First of all, is that, and moreover, the magnon has some like discontinuous features when you change the magnetic field. The magnon band has some transition, but you don't see that when you tune the magnetic field, you don't see anything strange here, right? So both of those reasons make us think it may be unrelated to magnon. And next, there will be one more reason to think that there is a phonon, that this is a phonon contribution by further experiments, right? So the puzzle is that it is very large, and and if we so if we compare the longitudinal and the Hall, we find that there's a ratio of a few hundreds, like 10 to the minus 3 kind of thing. And in these two materials, we chose to analyze this strontium titanate material first, because first of all, this material is simpler, so it's simpler for theoretical study. And moreover, the data is cleaner. The kappa L goes as TQ, as you would expect for a simple phonon thermal transport. And the kappa H goes as T4, also very clean data. That one is much more complicated. So we decided to understand this one first. Okay. Right. So let me summarize a little bit. The puzzle is this. The effect is linear in the magnetic field, so it seems it should be very simple to analyze. But the magnitude is order 1 in natural units, seems incompatible with the linearity in the magnetic field, because the magnetic field in the natural unit is 10 to the minus 4. So it's that seems to be very weird. And also, this is insulator. There's no obvious charge carrier that can couple to the magnetic field. As we just said, phonons are neutral, but if you have an iron crystal, the phonon motion can involve some motion of the sodium and the chloride ions, but that effect is way smaller than this, right? So these are the puzzles. So yeah, first of all, we want to confirm that it's the phonons that carries the heat. And why is that? So first of all, there is a very good reason to think whether phonons are relevant, because in all these materials, which are gapped insulators, there's one ubiquitous gapless degree of freedom, which is acoustic phonon. And they were, as we said, they were neglected in thermal Hall discussions because they are not charged. So the contribution is very tiny, like in sodium chloride, 10 to the minus 10 Hall angle. And in the STO experiment, the effect has been quickly attributed to the phonons, both by the experimental team and by us, and I'll explain why soon. And in the LCO, initially the phonons were excluded by the experimental team. But we argued about this possibility, and we communicated with the experimental team, and in the later experiment confirmed that it comes from a phonons. And let me emphasize this later experiment that confirms this phonon even in LCO. So LCO is the cuprate material is a layered material where each layer looks something like this in the C direction. Okay, it's a layered material. So all the interesting cuprate things happens as a quasi-2D system, which means the electronic degrees of freedom are quasi-2D. However, they did the Hall effect, thermal Hall transport in all three directions of the three-dimensional material, and they found all three directions looks almost the same, which means the quasi-2D feature of the cuprate does not matter here. That means that the only possibility should be the phonon, because only the phonon is the 3D thing in this material. Okay? So, right. So the question now becomes, what physics makes phonon couple strongly to the magnetic field, even though they are neutral, so that they can make the thermal Hall very large? And of course, we can have two vague ideas. The first idea is, okay, maybe there's some very large parameter in the material, so that even though if you expect the effect to be small, but due to a very large parameter, it turns out to be large. And the second is maybe the phonons strongly scatter with some material. So then, because phonons themselves may not couple that strongly to the magnetic field, but maybe they also interact with some other degree of freedom, so then help the process somehow. So those are two directions of thinking. And of course, this direction of thinking is very material specific, right? It depends on whether material really has some large parameter somehow. But this idea will be more general, right? But these are the two ideas that we'll explore. And it turns out that our phenomenological theory for STO involves both ideas. And because, as we just said, STO is simpler to study, that was our first phenomenological study among these experiments. So let's first look at the large parameter side of STO. So the large parameter comes from the fact that one notable material property of STO is that it's near ferroelectricity. It's not ferroelectricity, but it's near there. For example, you can look at a phase diagram where you have some quantum tuning parameter, such as you can exert some strain on the material, or you can do some isotope replacement. And just by doing some minor things, you can turn the STO from a paraelectric material to a ferroelectric material, which means it's very close to ferroelectric transition. So because of this, it has a large parameter, which is the dielectric constant is very large, because that means the charges are the positive and negative charge in the unit cell are very easy to move. And it turns out that in low temperatures, the dielectric constant is 20,000. So indeed, there is a very large parameter here. Okay, so how does a large parameter might help with the thermal Hall effect? So it turns out that a large dielectric constant will lead to a large flexoelectric effect, which I'll explain in the next slide. And the flexoelectric effect is to produce a large polarization. And because polarization is electric charge, right? So electric charge, the motion of electric charge can couple to a magnetic field. It's captured by this term in the Lagrangian, or say in the Hamiltonian, where the Lorentz force can be expressed like this: a polarization, and when the acoustic phonon motion has a u dot when it's moving and it has a polarization, it will generate a Lorentz force of this form in the Lagrangian. So the Lagrangian will have the usual terms for the phonon as well as this term due to the Lorentz force of the polarization. And the flexoelectric effect means when there is some acoustic deformation, like second order gradient of the U, the acoustic displacement, it will generate polarization, and it's proportional to dielectric constant. Why is there such a constitutive relation? We can look at a more pictorial way. So if you have a material that originally looked like this, the positive and negative ion look like this, and if you bend it, then there will be a relative motion between the positive and negative charge center. So that will generate a polarization. And when the dielectric constant is large, intuitively the positive and negative charge will more easily get separated. So that's why the large dielectric constant will generate a large flexoelectric effect. And you can measure this effect in the STO. And indeed, you will confirm that there is some coefficient that is of the order of the volts, right? It's the usual number. The condensed matter things usually have a unit of volts. But then there's this large coefficient, which is 20,000 in STO.
Sorry.
Right.
Could you explain this term in the Hamiltonian again, this B dot?
Right. It's just the Lorentz force. So the Lorentz force should have some term in the Lagrangian. So it's like A times X dot.
Okay.
Right. Like charge Q times A times X dot in the Lagrangian. And if the charge comes in the form of a polarization, then you can find that it looks like this.
Okay.
Yeah. Right. So so the large dielectric constant leads to a large flexoelectric effect. In the physical picture is very intuitive. Right. So then it comes back to here. It will generate a large coupling to the magnetic field of the phonon. So maybe this will produce a large time reversal odd Berry curvature, right? So the Berry curvature is when different components of U's are mixed and you need to re-diagonalize the Hamiltonian or the Lagrangian. So this seems like this will couple strongly to the magnetic field, so it will generate some large Berry curvature for the longitudinal and the transverse modes of the acoustic phonon. Right. So maybe then this Berry curvature, because it's the time reversal odd due to the magnetic field, then maybe it will generate a large thermal Hall effect. And it turns out this scenario has already been studied on a theoretical background by these people, not in this particular experiment context. We can use their general theoretical result in this particular context. So what we found is that this intrinsic Berry curvature contribution, even after the enhancement of 20,000 from the dielectric constant, it's still smaller than the observation by a few orders of magnitude. Let's see, roughly speaking, why that is the case. So let's compute the Berry curvature. Let's estimate the Berry curvature contribution to the Hall angle, the kappa h over kappa L. And it turns out that the estimation is right. Even if you do the actual calculation, it agrees with this estimation. The Hall angle due to the Berry curvature will be proportional to the time reversal odd part of the Lagrangian versus the time reversal even part of the Lagrangian. And the time reversal even part of the Lagrangian is this usual terms of the phonon, and the time reversal odd part is this. And if you take the ratio, you will find the ratio looks like this, where you have a time derivative because there's a u dot here. And how do you estimate the time derivative? It turns out that time derivative should be estimated as a v over the mean free path L. Why is that? Because the intrinsic Berry phase effect should be independent of the mean free path. But the longitudinal transport, as we know, should be proportional to the mean free path. So this partial T will estimate it by the phonon velocity versus the mean free path. And then if you use this and then you can organize the numbers into the product of 4 dimensionless numbers. And if you estimate these dimensionless numbers, we set this 10 to the minus 4. This is very large, 10 to the 4th, right? So they roughly speaking cancel out. But this turns out to be a small number, 10 to the minus 3 or something. And also A divided by L is also a small number because the mean free path is usually of the order of microns, but this is of the order of angstroms, right? So this is again a small number. So if you do the actual estimation, you'll find that the whole angle is about 10 to the minus 6 or 10 to the minus 7, which is much smaller than the measured whole angle, which is 10 to the minus 3. But it's already much larger than the usual insulator, which is 10 to the minus 10. And it's much larger than usual insulator because in usual insulator, this number is order 1, but now in this material it's 20,000. So it's already much larger than in the usual insulator, but still too small compared to the experiment. And also, if you look at the temperature scaling, because kappa L goes as T cubed, and this does not involve the temperature. So the kappa H will also go as T cubed. But in a previous slide, I showed that the kappa H in this material goes as T4. So it also doesn't agree.
Let's say like K, the elasticity will depend on temperature, right?
Right, but to the zeroth order, it doesn't. It's not proportional to empty. Right. Yes.
Sorry, I have this question, maybe it's strange, but usually in these materials which are close to ferroelectric transitions,
Right.
the optical phonons can have also small energies,
Right.
say softening, etc.
Right.
And here you consider on the acoustic part, which is the elasticity theory. What about possible impact of
Right. That's a very good question. That's a very good question. In fact, I simplify the story a little bit. This polarization and this constitutive relation can be understood as a mixing, like a rediagonalization between the acoustic and the optical. Right. So because the optical phonon will involve the relative motion of the positive and negative charge. So actually this comes from the optical phonon.
Oh, okay.
Yes, it's that is an effect like that. It's like a rediagonalization between the acoustic and the optical, right? But the optical phonons themselves do not directly contribute because even if the gap is small, the gap is still 20 Kelvin. But the experiment you can see the effect at like a few Kelvin, like 1, 2, 3 Kelvin, right?
So this U is into both optical and elastic.
It's rediagonalized, and actually the large coefficient chi here is related to the fact that it's because the mixing becomes enhanced because of the small gap of the optical phonon. Yeah, we can also phrase it that way. Yeah.
I question you. If like this system is cubic,
It's what?
original STO is a cubic,
Yes.
but do any experiments depend on the 001 direction?
We will relate to that. Yeah, actually, this is also a very good question because we just found this effect is too small. So this effect cannot explain everything. So we will go to that direction. Yes. Right. So this Berry phase effect intrinsic is not so small. And this is something I want to emphasize. And people have been trying to look for intrinsic thermal Hall effect of phonons. And usually they are this small. And even with this large enhancement, it's still very small. So far, I don't think in any material we have observed the intrinsic phonon Berry curvature thermal Hall effect, right? Even if this large chi is still too small, right? So there have been many proposals trying different ideas, but they are always this small. There were some wrong proposals saying it would work, but it would not. That's something I really want to emphasize. That's why we need to consider something beyond just the intrinsic Berry curvature contribution. So let's also use the other idea of strong scattering. And it turns out that STO indeed has this material property that allows the possibility of strong scattering. And it's because STO at low temperature has structural domain walls. Right, so below 105K, because our experience is 5K or so, so it's well below this. this cubic lattice will become trigonal. It's related to what you said. Well, this is exaggerated, but it has this. And because of this, there will be this twin boundary domain walls, where the elongated directions in different domains are in different directions. Okay, so they will generate these domain walls due to this transition. Okay, so in low temperatures, there are indeed these domains and domain walls, and the domain size is of the micron scale. And you might recall that I mentioned something else is also the micron scale, and it's the mean free path in this material is micron scale. So the Benias group measured the longitudinal thermal conductivity. The longitudinal data shows that phonons indeed scatter strongly against the domain walls, so that when the domain wall separation is micron, the mean free path is also micron, which means the scattering probability of the phonons against the domain wall is of order 1, or which means the scattering angle, typical scattering angle, is order 1 of the phonons of the domain walls. Okay? So indeed, there is a strong scattering. But now we want some time reversal odd effect. So we not only need a strong scattering, we need the strong scattering to have some time reversal odd effect. And it's a skew scattering. What is a skew scattering? The idea is very simple. If a scattering process and the time reverse process have unequal probability, then it's called a skew scattering component. Like the unequal part is called a skew scattering. And in particular, we can use a Boltzmann equation to analyze a phenomenological Boltzmann equation to analyze a strong skew scattering of the phonons. And so we will introduce some, I will not go into the details, but we will introduce some phenomenological parameter A, which is dimensionless, and strong scattering, a strong skew scattering means the typical scattering angle and A are both of order 1. Okay, that's what we mean. And then we just phenomenologically propose such a Boltzmann equation. And without going into the details, I will claim that with phenomenological parameter A of order 1 and combined with the large dielectric constant STO, we will be able to reproduce the observed Hall angle, 10 to the minus 3 Hall angle. And we find that indeed the extrinsic effect is about 10 to the minus 3 times larger than the intrinsic effect. And why is that? It turns out that it's because there's an extra enhancement from the mean free path over the lattice scale.
So how you relate this parameter to the magnetic field?
Oh, it's because the phonons themselves have a large Berry curvature due to this large number. And with a large Berry curvature, when it occurs, a skew scattering when a strong scattering occurs, the skew component will also be strong.
I see. So you combine the Berry curvature of phonon with
a strong scattering. Right. So the Berry curvature, the large Berry curvature has this enhancement, and the skew scattering has this enhancement. Right. As with these two enhancements, we can explain the effect. And moreover, this explanation is compatible with other qualitative evidences in the experiment, whose details I'm not going into.
Do you have some intuitive explanation why this skew scattering is really large and really light?
Right. We think it's because the Berry curvature is large and also the scattering is strong. So we combine the effect of both, and yeah, it's just as simple as that. So we don't have a detailed mechanism for how the scattering occurs.
We can study more models this.
Right, because the twin boundary is very complicated. Like in this twin boundary, it's proposed that there are some weird degrees of freedom living on the twin boundary that has not been very well studied. But based on the phenomenological data coming from this group, it's concluded that the phonons does not simply goes through with a refraction or reflection on the twin boundary. It has very strong scattering at the twin boundary, but we don't know how at this point. And we don't need to model how. We just need to know it's a strong scattering. It's sufficient to explain with very mild assumption.
So do you expect that with higher temperatures, the domain will appear more frequently?
The domain walls are mostly frozen. Right. So that depends on the cooling process, how you do the cooling process. But once it's formed, it does not change with temperature. in this case, yeah.
Yeah, but the correlation length, so this L will be different at different temperatures, yes?
Because they are frozen, so mostly not. It depends on your cooling scale. Like how your cooling protocol, how you cool the material. Yeah, that's actually one of our experimental proposal later. We want to reassure the rule of domain walls by maybe cooling it under different conditions so that you form different domain sizes and see whether it agrees with our explanation. And also another thing we can check is if we somehow tune the material so that it goes further towards the ferroelectric criticality, what happens? Those are the predictions that we
But
can
isn't that right that if you change temperatures, then at large temperatures, the domain size is very small and the smaller
they are mostly
is
frozen.
bigger and bigger?
They are frozen. These are not like very easily moved domains, it turns out. Right. In the later part, in another material, we'll propose some domains which are easily moved. So these two kinds of domains, some domains are easily frozen, some other domains are easily moved as you change the temperature. That's like the previous case is like a permanent magnet. Like in a permanent magnet, there are these magnetic domains which don't easily move. But there are some other ferromagnets, like iron itself. The iron is a ferromagnet, but it's not used as a permanent magnet because domain was very easily moved. So both cases are possible. And it turns out that the structural domains in STO are frozen.
So in this case, result would be sample dependent, but temperature dependent would be universal.
Yes, it turns out this is a good evidence. Yeah, so we want to control the sample dependence by cooling under different conditions to see the rule of the domain walls. That's one of our proposals. Right. Okay, so these are...
Sorry, another stupid question.
No, it's
just to discuss. So if you apply electric field from the very beginning and cool down your sample, you will left without the scattering mechanism. And at the end of the day, there won't be any effect. It's very simple to check experimentally.
This is still paraelectric.
I apply electric field,
Right.
and then I have one domain in my sample.
No, the domain is not the ferroelectric domain, it's the structural domain.
Structural domain.
Right. The domain is...
that's okay, now I see.
Yeah, the domain is... Oh, sorry, I go to for sorry.
I thought it's just the ferroelectric domains.
No, the domains are this. Like the cubic lattice becomes longer in one direction. It's independent from ferroelectricity. Right. Okay. So for STO, we successfully explained the thermal transport and also compatible with other qualitative evidences. So after this experimental work and our phenomenological work, phonon has become a main idea in trying to explain the large thermal Hall in various insulators. At the beginning, people try to think in terms of other things, but after that, people start to think about phonons. But then this leads to the question. The very large parameter is only applicable to some special materials like STO. So for other materials, maybe we need to only rely on strong scattering. So in the remaining of the talk, let's consider strong scattering, which is a more general mechanism. Right. So this is the purpose. That strong scattering is probably worth more study. So in particular, the next part I want to talk about resonance skew scattering. Again, we need skew scattering because we want a time reversal odd effect. And now we want to explain, we want to explore the idea of resonance. And why resonance is very interesting, right? Because we want to ask a question. In general, what makes strong phonon scattering possible? In general, at low temperatures, phonons have very low energy and very long wavelength, right? Because they are gapless. So low energy means long wavelength. So a simple point effect would not scatter phonons strongly because something with long wavelengths would just diffract through a point effect. That means to strongly scatter phonons, we need two possibilities. One of the two possibilities. One is maybe there's some low energy degree of freedom, such as a dynamical defect or some other low energy degree of freedom, so that they can couple with the low energy of the phonon, then form some kind of resonance. That's one possibility. The other possibility is we have some expanded formation, some large size thing, so that can go with the long wavelength of the phonon, such as a domain wall that we just saw in STO. So because the phonons are low energy and long wavelengths, to scatter the phonon, we either need something of low energy or something with large size, okay? And at least in STO, we saw that there's a domain wall. Actually, in STO, we need both, but the main thing is the domain wall. So we now try to, but we know that in LCO, there should be no structural domain wall. So we try to explore this possibility. Maybe there's some low energy degree of freedom that resonance scattering occurs. Then maybe that's a possible explanation for LCO. Even if it's not the mechanism for LCO, it's some in principle, some mechanism that is worth exploring in general. So now let's explore the idea of resonance skew scattering. So the idea of resonance scattering, not skew scattering, just usual resonance scattering, became important because of Anderson, Halperin, and Varma's famous work on the thermal properties of glasses. In the glasses, you know, glasses are very complicated materials. They have a lot of defects at all energy scales. So in particular, they will include some dynamical defect at low energies. Okay, so then there are some two-level system defects, for example. And if the two levels turn out to match with the energy of certain phonons, then there will be resonance. And then the resonance scattering of phonons with this dynamical defect in the glasses will produce interesting thermal transport behavior. And this has had a very important impact in the field of thermal transport. Okay. So now what we want to generalize is we do not just want non-skew scattering that are under resonance. We also want to consider resonance skew scattering. And first of all, we want to mention that this kind of physical picture may really be relevant in LCO. Why? Because LCO also has some glassiness feature. LCO is also a relatively complicated material. It has some glassiness in different sectors of the material. So it's natural to expect that it might involve a lot of dynamical defects.
Sorry, could you maybe comment more about it? In what sense there is a glassiness?
Like there are spin glassiness and so on. Right. Right. Moreover, if we look at the low temperature longitudinal conductivity, the black dots, you can see that it's not TQ. The power is smaller than TQ. And that is also a feature that is compatible with the Anderson, Halperin, Varma. So maybe there's some kind of defect that makes the phonon longitudinal transport lower power than TQ. Okay, so that's some evidence that maybe we really should consider dynamical defect in LCO.
So we consider the resonance such that it has the energy we distribute to the own rank, right?
Yeah, so there is some energy distribution at different various energies, so they can resonate with different phonons. Yes. Right.
I can't tell you, in your, what kind of defect you consider?
We will mention that. We will talk about that. Yeah. Right. So, but the idea is maybe it's relevant in LCO. Right. So if we can indeed identify the dynamical defects in the cuprates, it will be very useful for understanding in general cuprates material property. So this is what we want to propose to experimentally, is that the phonon thermal Hall, although they are carried by phonons, not some exotic thing, but maybe they can help us to understand the material property better. Okay, so let's see what kind of mechanism can generate a resonance skew scattering. So this is an Anderson, Halperin, Varma resonance scattering. It enhances regular scattering. To enhance resonance skew scattering, you need a situation like this, because you need time reversal oddness So you can have some ground state of the defect and some excited state of the defect, such that there are two excited states that are splitted by the magnetic field. So the time reversal oddness come in. And moreover, the two defects have some decay width like this. So within this range of the decay width, the phonons can have resonance within such a wide range of decay. So both states can resonate with the phonons, but with slightly different energies.
But in this case, you don't need very curvature phonon.
Right. That's a very important point. Because in the previous STO example, the Berry curvature is large only because dielectric constant is large. But now in general materials, there's no large Berry curvature. So we should not rely on large Berry curvature. Right. So we should rely on this mechanism. So the skew scattering need to keep track of the angle, right? Because the skew means it depends on the angle. So you need to keep track of the angle. And the difference in the energy actually will help you keep track of the angle. And because the difference is related to the magnetic field. So you will keep track of the time reversal all part of the angles. And so now that the energies are slightly different, there will be interference. Interference will keep track of the angle. And in more detail, we can consider situations like this. Like in this traditional two-state systems, you can consider, for example, there's a defect where some charge center can either be at this position or that position. So that forms a two-state system. And so this is some dynamical defect that can generate this. So for resonance skew scattering, you can consider, for example, LCO has a C4 lattice symmetry. So we can consider some defect where some charge center, for example, can be at one of the four positions, not very well aligned with the lattice, but there are four positions that are equally likely. Okay, and then at this four position, it can have an angular momentum 0, plus, minus 1, or 2. And angular momentum is well defined mod 4. And then the B split will be between the L equal to +1 and -1, right? And because they have different angular momentum, they should be able to keep track of the angle. And the interference between these two slightly different energies can generate this resonance skew scattering. So that's a kind of physical picture of the defect. And remarkably, we can show that the resonance skew scattering amplitude is for a range of parameters independent of the coupling to the leading order. So that's a feature of resonance. So resonance means it doesn't really depend too much on how much you drive it. Right. So it's independent of the coupling, makes it very large. And moreover, the smaller the decay width is, as long as the decay width is larger than the split, but the smaller the decay width is, the larger the amplitude will be. And we can roughly see why. To calculate the skew scattering probability is you compute the amplitude and look at the resonance component of so you take so probability is amplitude squared, right? And the interference comes from the intermediate state being different defect state. So the N state, for example, is this one and the M state is this one. So that's the interference in the computation of the quantum probability. And then you can see that if you do a dimensional analysis, you'll find, first of all, it should be proportional to the time reversal odd parameter, which is the magnetic field split of the energies. And it should also be proportional to the width of the resonance, because only for phonons within the range of the width can have resonance scattering. So it should also be proportional to the width. And it should be proportional to the coupling constant of 4, because in the calculation of the amplitude, the phonon needs to be absorbed first and then emitted. Right, and then you take the square to get the probability, so you have G4. And also the intermediate state has its own Green's function, and because you take them square, so it has a square. And it will be approximated like something like this. And then you found that there is a G-force over gamma squared. But the width gamma also comes from the intermediate state emitting and reabsorbing a phonon. So it's proportional to G squared at leading order. So overall, the resonance skew scattering is independent of the coupling constant between the phonon and the defect. So even if the coupling is small, because of the resonance, the effect can be large.
Basic diagram, is it using the optical theorem?
Somewhat like that, yes. Right, so these are some remarkable features of this mechanism. And right, so we constructed as we drew this C4 lattice symmetry picture. And if we assume some reasonable parameters, we can get a large thermal Hall of the observed scale. So then it means we can reproduce this effect with reasonable parameters. But so this is motivated by LCO, but unlike in STO, which we are pretty sure our explanation is to leading order correct. Here we do not claim that this is the right mechanism for LCO, but it's motivated by LCO and it gives reasonable result. But whether it's the correct phenomenology should be supported by future experiments. For example, by trying to directly detect this defect in using other methods. Right. But nonetheless, our model is a non-trivial proof of the concept that with the
Sorry, you mentioned that the temperature dependence is different from STO case, and how can we see it, from example, from the previous slide?
Right. So here it's because it has a glassiness. So in general will have a low power on the temperature. Right. Yeah. So I can tell you the details afterwards, right?
Okay.
Yeah, but in general, just more dynamics will lower the power in temperature, right? Right. So this is a non-trivial proof of concept that resonance skew scattering can produce large effect even without large parameters. So I think maybe this model is just a specific model, but this general idea we think is valuable for general study of thermal Hall phenomenology. Right.
In this model, defect level is captive, right?
So
Defect level is a captive state.
this
Captive, right?
Gap is a delta
Yeah.
state.
so
Captive state. The temperature dependence is related to
the gap of the state.
size of the gap.
Yeah, but because these are defects, you can assume that the gap has a distribution. That there is some probability that the gap is this value, some probability the gap is that value. Just like in the Anderson, Halperin-Balmer work on glass. Right.
Gap energy is what,
So the gap of the defect is a random variable.
but this size is more less than phonon dispersion energy.
Right. Because the temperature is low, as you assume the distribution of the gap is extended over a range that is larger than the temperature, it is okay. Doesn't have to go to the Debye energy scale. It's only larger than the temperature scale, right? It has a distribution of the gap energy that is larger than the temperature scale. Right. Right. So overall, let's come back to this general idea. So now that after this phenomenological study, it turns out that the study of thermal Hall effect in this insulating material come to the story of what makes the strong phonon scattering possible. And for low temperatures phonons, we need to consider either low energy degree of freedom or extended defects. Okay, and this is what we learned from this material. And since I am running out of time, I'm not sure if I should talk more about this.
Like 7 more minutes.
7 more minutes?
Yeah.
Okay.
Can I ask a question?
Yes.
Before we move ahead? So I understood that in the case of STO, the defect was coming from the main wall.
Right.
Here, how do you get the defect exactly?
Right, we don't exactly know because LCO is very complicated. But this picture, you can think, for example, there is some ion whose position is not exactly at the right position that it wants to be, so that it can be at one of the 4 positions due to the C4 symmetry of the material.
Okay.
And right, so then
But so if you have C4, then there should be 4 states?
right, there is an upper one which is irrelevant.
Okay.
Right. Good. But we are not saying this is the mechanism and LCO is motivated by that. But we view this as a proof of concept that just even a simple model like that can create a large skew scattering without large parameter.
And why didn't you consider such resonant effects in the case of the earlier material,
The
STO?
STO?
Yeah.
It can have, but it just didn't need to have that because there's an obvious reason that there is strong scattering from the twin boundary. So it doesn't have to have defects like this. But it maybe on the twin boundary, there's something like this because it's widely believed that, maybe not widely, but it's speculated by some experiment that on the twin boundary, there are indeed some low energy degrees of freedom, but we don't know the details, right? So this is a proof of concept.
And
right.
also the value of this K that you are calculating. So are they comparable?
What K?
The
kappa?
kappa, yeah, exactly.
Right, so with reasonable parameters, we can generate the value comparable to the experimental observation.
No, I meant
In LCO and STO,
yeah.
yeah, they are of the same order of magnitude.
Okay.
Right.
Okay.
A little bit larger in STO, but same order. Okay, so right. So yeah, so by the phenomenological study of this, we start with some very mysterious observations in these materials where people try to come up with very exotic explanation, and then we and maybe some experimenters gradually led people to think, okay, phonons can actually be more interesting than naively expected, and then maybe their interactions with low energy defects or large effects are in general worth studying. And later, we are also applying this general philosophy to the longitudinal and thermal transport of this alpha ruthenium trichloride. Okay, let's briefly talk about this for about, like, say, 5 minutes or so. Yeah. So it's a candidate material for Kitaev spin liquid, and it's a quasi-2D material with different layers. Okay, and in each layer, there's some Kitaev term, but because there are also the Heisenberg term of the spin and so on, so it's not necessarily a spin liquid. Most likely it is not. But at least it has a Kitaev term in the spin sector, means the spins are not a usual simple ferromagnet or anti-ferromagnet. The spins has a very strong frustration among themselves. So that's an important material property that we need to remember, that the spin degrees of freedom are complicated and has strong frustration. Right. Okay, so there are two puzzles from the thermal transport since 2018. One is a large thermal Hall effect, also a very large thermal Hall effect. And this is not the very first data, but this is one of the first nice data by On's group. And another puzzle is the longitudinal thermal transport also has a puzzle now. It is that if you tune the magnetic field, you see the longitudinal thermal transport have very obvious oscillation between, say, 0.4 Kelvin and 4 Kelvin. Okay, above 4 Kelvin, it goes away. But at very low temperature, it has this very obvious feature. This certainly is very strange and needs some explanation.
But another explanation is there are a lot of transition temperature.
Transition temperature.
The transition crystal field. There are too many crystal fields.
Right. It will be related to that.
Not the oscillation, is it?
Right. Yeah, so our explanation will be along that direction. But we need to go to more details. Which transitions and right. So there are different, maybe there are different transitions or, yeah, so we will go into that direction. But at the beginning, it's very puzzling. People think it's oscillation. Indeed, we don't agree with that, right? But thank you. We will go into that direction. Okay, so the large thermal Hall is again very large, the order 1 in the natural unit. So this is the natural unit, and it's order 1 in the natural unit. But it's different from the previous STO and LCO. In the STO and LCO, at low temperature, it has some power scaling with the temperature. Here, it's suppressed at low temperature and only start to ramp up at around 5 to 10 Kelvin. So, and moreover, some early experiment claim to have observed a quantized, like half quantized thermal Hall. And now from this newer data, you can see that it's nothing quantized at all. Okay, but the early experiment, they try to claim something very big. So they try to claim it's quantized, but really
more
it's not.
buzz around.
Right. So, but the puzzle is that it's unlike STO and LCO. The puzzle is a very large, but maybe different mechanism. And indeed, the data is consistent with the bosonic trend band of a 10 Kelvin gap magnon. So that's related to your earlier question. So magnons is proposed by Yung-Bakim's group and maybe others. So this data is consistent with the bosonic trend band of a 10 Kelvin magnon. Okay, so we think this is a plausible explanation. So we will not directly explain this, but our explanation for the longitudinal will have a relation to this, as I'll explain later. But this is not our work. So the longitudinal looks very strange. It looks oscillation and seems more mysterious. And indeed, at the beginning, people thought, okay, maybe there's something very exotic, spin liquid quantum oscillation or anything. But it's very unlikely, correct? For two reasons. First, it's inconsistent of the phase diagram. Because in the phase diagram at low temperature, this part is very well understood. The spins just have a magnetic order. And this part, the spins just all point to the same direction with the magnetic field. Okay? And only in this intermediate magnetic field part, the state is not very well understood. Maybe a quantum spin liquid. But you can see that there are features even before coming into this regime. Okay, so before coming into this regime, there should be nothing weird. Moreover, even if they come up with this spin liquid quantum oscillation to produce this period, this kind of period in the magnetic field, it turns out that they need to have some very weird claim. Like there's some emergent magnetic field that is proportional to the actual magnetic field, but a few hundred times larger. Very weird claims. So even if they use quantum spin liquid or whatever, there's no good explanation. So by looking at more data, this is data by the same group, but another sample, we can find that the dips are still there, but it has very strong sample dependence. So this will suggest that it's phonons. And moreover, it's a phonon scattering with a spin degrees of freedom. Why is the phonon scattering with a spin degree of freedom? Because as we can see, the one common feature of the data, although the details are different, one common feature is that in the intermediate magnetic field, the kappa is smaller than at large magnetic field, right? And at large magnetic field, the spins are all frozen in the direction of the magnetic field. So the spins are doing nothing. In that case, the kappa is larger. And moreover, in the large magnetic field, you can see it goes as the T cube of the phonons. So what does this suggest? This suggests that at lower magnetic fields, the phonons are interacting with the spins, so that it reduces the phonon thermal conductivity. Because at larger magnetic field, the spins are frozen. The interaction becomes weaker.
But in the dual system is not spin half. This is J effective half. We are coupling between J steady half and half is coupled. The kind of unblack line.
Right. So the phonons in general, the spins will couple with.
Spin degrowth is not the project. You think about the bambling like coupling or high energy J half with the J half.
I think it can be simpler. It's just like if you have two spins on neighboring side interacting, and a phonon comes and their distance changes.
G tensor is not diagonalized with J half and J half. Both diagonal G tensor is.
Yeah, but maybe let's see the later slides and yeah. So, but this suggests that the phonons may be interacting with the spins, giving these suppressions, and maybe the dips are because the suppressions are somewhat stronger. And if we look at the further data by other experimental groups, then we note two features. First is, as you just suggested, it turns out that these two dips coincide with the places with high magnetic susceptibility. And this higher magnetic susceptibility is because the spin sector has some second order phase transition that is well understood. Some spin order changes slightly. And it turns out these two dips coincide with that. So this strongly suggests that these two effects are related. But there are some other two dips, these two other dips that does not seem to coincide with any phase transition. However, these two other dips also have some interesting new data. That is, if you go to even lower temperature, 0.25 Kelvin, it seems like they start to go away. This suggests that these two dips and those two dips comes from different mechanisms. Okay, right. So again, we come back to this picture: low temperature phonons and low energy and long wavelength. So the low energy degree of freedom explanation is already involved in the first two dips, right? There's a second order phase transition in the spins, which have some critical fluctuation, which is low energy, and that might have some resonance with phonons, whose details I'm not going into. It's very possible that it will create some dips because the interaction is stronger at the phase transition. Right. The crucial part is to explain these other two dips. It's a more non-trivial. So we propose this related to extend deformation. We also tried some other low energy degree of freedom and we excluded. Well, I'm not going to explain how. But we tried the explanation of extend deformation. That is scattering with the long wavelength phonon. But what extend deformation? It turns out that we propose a very simple mechanism. That is the simplest mechanism we can think of that is compatible with all the experiments so far. So we propose that because this is a highly frustrated spin material, in the intermediate magnetic field regime, there can be some competition of low energy spin states because it's highly frustrated. And as you tune the magnetic field, you can imagine a scenario where the energy density of one state is lower for some magnetic field, but that of the other state is lower for some other magnetic field. You can imagine a scenario like this. And because they are competing low energy spin states at finite temperatures, there will be fluctuation of domains, right? Just like in an Ising model, there will be some fluctuation of domains. So there will be some formation of domains. And if we just analyze the domains, we assume the domains are of micron scales, and then the phonons will have refraction, maybe other scatterings across the domain walls. And this will be sufficient to give the expected suppression. And as we can see from the data, the suppression is by a factor of about one half or lower. Okay. So with reasonable assumption about the domains, this can give the reasonable suppression. And moreover, it's consistent with the fact that these two dips go away at low temperature, right? So these two dips comes from when the two energies are closest. In that case, there will be the most domain walls. And the two dips will become harder to see at low temperature because as the temperatures becomes lower and lower, the thermal fluctuation becomes smaller, so there will be fewer domain wall fluctuations. So this is consistent with that. Moreover, it's consistent with other experimental data, such as the heat capacity. Because now you have the thermal fluctuation of the domain wall fluctuation, then you need to care about their thermal conductivity, thermal capacity contribution, and we found it's also consistent with the data. And moreover, this is compatible with Jung-Kim's model for thermal Hall magma and Chen band, because in that model they needed the frustration, and then it will have a lot of competing low energy states. Maybe not exactly their competing low energy states, but at least it's compatible with theirs. So it's also compatible with the thermal Hall theory. So we find this is a simplest, really very simple explanation, but we excluded a lot of other possibilities and found this is the simplest possible explanation. But one can ask, what is the nature of the competing states? Are they those of the Jung-Kim's simple mean field model? Maybe not, because mean field theory should not apply here. We don't know what are the competing states, but just having competing states is sufficient to explain the data. And to understand what might be the competing state, we need further experiment. And we can also propose some further experiments that can try to confirm this picture of competing states.
So to conclude now.
Yeah. So the conclusion is we already concluded before that these are the general pictures. So so the general idea is that energy is a universal transport, so it detects more interesting things. But the difficulty is you need to do the phenomenological analysis more carefully. And our goal is to make the thermal transport a better established approach in the years to come. Okay, thank you for the extended time for me.
Yeah. So in the
last slide show this longitudinal dip
Yes.
in the longitudinal flow part.
Uh-huh.
So if you consider the magnon contribution to the thermal or like to the thermal transport,
Uh-huh.
then it does not explain, right?
Right, so the magnon has a gap, right? That's a very good point. Let's emphasize this point. So, so these two data, this we think the magnon explanation is very plausible, and this we think is phonon interacting with some other things.
What about
Right.
magnon?
Right,
Magnon
and
plus phonon?
right. So you can see that these two phenomena occur at different temperatures. These start to ramp up above like 4 or 5 Kelvin. And this effect is not shown in this picture, but this effect will go away above 4 Kelvin. So these are two different temperature regimes. But we find a connection between them. That is in the magnon theory here and in the competing state theory proposed by us here, both of them need a very strong frustrated competing state. That part is compatible.
You think about the endpoint magnon, not the endpoint magnon. Endpoint phonon is very, gap is almost zero near the critical region.
Oh, is it?
My calculation.
Oh, is it? I see. Maybe we should discuss more because I didn't know about that. Let's maybe discuss more after the talk. I'm here until Friday. Yeah.
So I have another question. So you said that here, so can I think of these fluctuations as some sort of defect or not? Like the mechanism?
Right. So as you can see, this domain wall formation, you can think of them as defects, but those are defects coming from dynamical degrees of freedom.
But that was there, that's how you explained or that was the mechanism introduced by Anderson, Halperin, and Verma, as I understood, no?
No, those are point defects. These are extended defects.
Okay.
Right. So those are dynamical defects, but with low energy. Here is the scattering is strong. They come from dynamical degrees of freedom, but the scattering is strong not because of dynamical resonance, but because the defects are just large. They are micron scale. So the phonons
But
cannot
then
diffract.
what I got confused with was that you mentioned that in the earlier examples,
Right.
because of the resonant scattering,
Right.
the value of kappa was large. Yeah. Wasn't that what you said?
No, it's not that the value of kappa is large, but the temperature scale of kappa, the temperature scaling of kappa is lower than TQ.
Okay. So
Right.
I see.
Here in this material, in this large magnetic field part, it goes roughly like TQ. In this part, the temperature dependence is more complicated. Yeah.
And another question was that, so for this second, like the last part, ruthenium chloride, here, can you do a similar Boltzmann equation type analysis or no?
Yes, but it's yeah, we can do that, but it's so let's say this for this is even simpler than Boltzmann equation, but even with refraction only, it can generate a sufficiently large effect. So this is like middle school physics. But of course, to come up with this right idea, you need to go beyond middle school. But refraction is middle school physics, right? In the other two dips, like the scattering with those critical fluctuations, you need to combine both Boltzmann equation and hydrodynamics. Yeah.
Okay, so let's thank Jing-Yuan for this nice presentation. And if you have further questions,